In 2026, three physicists asked a question that sounds almost too simple for a serious science journal. What happens if you try to cut a single particle of light exactly in half and actually succeed? The answer they calculated was so strange that it briefly broke their own intuition about what light even is. First, the basics. A photon is not a tiny glowing marble. It is the smallest possible packet of electromagnetic energy, and that packet size is fixed by its frequency following Einstein's famous rule that energy equals a constant called h times the frequency. Einstein figured this out in 1905 while explaining the photoelectric effect, where light knocks electrons out of metal. Turning up the brightness of dim red light never ejects a single electron no matter how long you wait, but a single flash of blue light does it instantly. That only makes sense if light arrives in discrete chunks, each carrying a fixed dose of energy tied to its color, not its brightness. Turning up the brightness just sends more photons, not stronger ones, and each electron can only ever absorb one whole photon at a time. So if you fire one single photon at a half-silvered mirror, a beam splitter that reflects half the light and lets half through, what happens? Classically, you would expect it to split, half going one way, half the other. In 1986, physicists Philippe Grangier, Gerard Roget, and Alain Aspect actually tested this with real single photons and detectors on both sides. It never split. Every single time, the whole photon showed up at exactly one detector, never both, proving light really does travel and land as one indivisible click, not a divisible wave of energy. This anti-correlation was the smoking gun that photons are real, countable particles, not just a mathematical convenience. But here's where it gets interesting, because there's a completely different way to make one photon become two. Fire a high-energy photon into a special nonlinear crystal, and it can spontaneously convert into two lower-energy photons flying off in different directions. This is called spontaneous parametric downconversion, and it is not cutting a photon in half at all. The original photon is destroyed completely, and two brand new photons are created from scratch, with their combined energy and momentum forced to exactly match what the original photon carried. The two new photons come out entangled, meaning measuring one instantly tells you about the other, no matter how far apart they travel. This exact trick is what labs around the world use today to generate the entangled photon pairs behind quantum cryptography and quantum computing experiments. So downconversion makes new photons, it does not slice an old one. Which brings us back to the real question, the one nobody had rigorously worked out until this year. What if you tried to physically interrupt a single photon's wave packet mid-flight, chopping its wave in two the way you would cut a piece of string? Physicists Isak Rukun, Jan Gulla, and Johannes Skar at the University of Oslo modeled exactly this. They imagined a single photon reflecting off a mirror, then yanked the mirror away at the precise instant only part of the photon's wave had bounced back. Intuition says you would get two smaller, weaker half-photons flying off in opposite directions. Instead, the math produced something far stranger. A single, well-defined photon on one side and pure, empty vacuum on the other, with no in-between fragments at all, only a razor-thin transition zone connecting them. Underneath that clean appearance, the true quantum state is a bizarre superposition mixing every possible photon number at once, 0, 1, 2, all the way up toward infinity. A hidden complexity that only reveals its simple face when you actually measure it. The researchers stress this is not science fiction, since photons this long can stretch for meters or even kilometers, meaning the shutter does not need to be impossibly fast to test it in a real lab. So you cannot cut a photon in half, not really, but you can force it into revealing that the universe was never built out of solid little billiard balls in the first place. It is built out of probabilities, energy quanta, and fields that only look simple once somebody dares to look. If a single ray of light can hide infinite photons inside empty space, you have to wonder what other everyday things are secretly this strange. So subscribe if you want to find out.